So in this video, we're going to cover an introduction to organic chemistry, which is the last part of your lab. We're not doing any experiment about it, but this is definitely going to be included in your final exam, so pay attention, please. So we're going to start with the definition of organic chemistry. And the first definition that was created was that organic chemistry is the chemistry of carbon. However, in compounds like these, for example, diamond, you have only carbon here, but this compound is inorganic. In contrast, you have this plant here that contains other elements than carbon, and this one is considered organic. So what is the difference? There was a second definition or a second attempt to define organic chemistry, which is an organic compound contains a substantial amount of carbon and hydrogen. And this is true, absolutely true. However, it's a very incomplete definition. Years later, this guy, Friedrich Wöhler, he was working with urea, which is this molecule here, and he discovered that urea is also an organic compound, and if you see, it contains other elements different than hydrogen and carbon, right? So, based on his research, the most actual definition of organic chemistry was created, and this is: organic chemistry is a chemistry of carbon. So carbon is still a very important element in organic chemistry, it's the base. And carbon is an element that forms strong chemical bonds. And these strong chemical bonds are covalent bonds. Remember, covalent bonds are stronger than ionic bonds, right? Now, these bonds are formed between two carbons, or carbon can also be bonded to many other elements like hydrogen, oxygen, nitrogen, phosphorus, sulfur, and some of the halogens. Remember, the halogens are those compounds located in the group 7A in your periodic table, okay? All the way to the right, right before the noble gases, okay? Now, if we want to write the formula of an organic molecule, we are going to write first the carbon with the number of carbons here, right? And then hydrogen, and then if we have any other element present in the molecule, we are going to follow this order. First nitrogen, then oxygen, then phosphorus, then sulfur, then the halogens. And if you see, these guys here follow an alphabetic order, right? So carbon and hydrogen first because they are the main components, and then the other elements, okay? Now, organic compounds can be found everywhere. So for example, in carbohydrates, proteins, lipids, nucleic acid, these are part of any alive species, right? And if they are combined in certain order, they can form animals or seeds, grains, roots, vegetables, animal products, for example, milk, etc., etc., etc. Now, we can also find organic compounds in man-made products. For example, all these plastics here are made out of polymers, which at the end are a combination of organic compounds, right? So polyester, polystyrene, nylon, all of these polymers are made out of organic molecules, okay? We can also find them in medicine, for example. Aspirin, this is the formula of aspirin, acetyl salicylic acid. And in this case, this aspirin contains vitamin C. This is the formula of the vitamin C. And if you see, all of them are formed by carbon and by hydrogen, and they have oxygen too. Okay? All right. It is believed that over 16 million carbon-containing compounds are known now. So whatever you look at, there is an organic compound, right? And that's why organic chemistry is really important. Now let's give this brief summary about carbon. Carbon is an element or an atom that can form 4 covalent bonds. Why? Because it has 4 valence electrons. And remember, we have to fulfill the octet rule, which means it has to be combined with 4 more electrons, forming 4 covalent bonds. These other electrons can be can come from another carbon, or it can come from hydrogen, or from oxygen, or from the other atoms that we already covered in previous slides, okay? Now, we said that the bonds between carbon and either another carbon or another different atom is a strong bond. And we said that these bonds are covalent. Remember, covalent bonds are stronger than ionic bonds, and therefore the reactions between organic compounds are slower if we compare them with the reaction of ionic compounds. Okay? Now, hydrocarbons, and notice this, here we are talking about organic compounds that are only formed by hydrogen and carbon, okay? So this is a particular group of our organic compounds. These guys are non-polar, and of course, because if you remember, the electronegativity of hydrogen and the electronegativity of carbon is very similar. So they are considered non-polar. And therefore, they do not dissolve in polar solvents. Like, have you ever seen this? Water, if you remember, is the most polar component in the world, so at least in this world. So hydrocarbons or oils, for example, are not going to dissolve in water and any polar solvent, okay? Now, another characteristic is that they have low melting points due to weak intermolecular forces. And this just reminds me, for example, butter. You can put the butter in the freezer if you want, but as soon as you take it out, it's going to start getting softer. It's going to start melting, right? So the melting points in general are lower. And once again, due to weak intermolecular forces, because the only force present in hydrocarbons is the London dispersion force, okay? Now, to write organic molecules, we can use different type of formulas. The first one is what we call the molecular formula, and if you remember, you covered that in chemistry 1411, and we said the molecular formula is going to give me the real amount of the atoms present in that molecule. So for example, in here I have 1 carbon, 4 hydrogens, 1 oxygen. But it's not going to tell me anything about the structure, okay? Now, to represent the structure, we have the structural formula. In this formula, we can see how are those atoms here, how are they connected to each other. However, this representation is not going to tell me anything about the shape of my molecule. For that, we can use either a ball and stick model. If you remember your molecular geometry in 1411, this is the way we represent the molecules to find the shape. Or this type of formula can also be represented as a perspective drawing. This is a perspective drawing, and in this representation, we have, for example, this hydrogen, which is equivalent to this hydrogen, represented by this wedge, right? And this one that is completely full is telling me that this hydrogen is pointing to the front. towards you, like this one. This other representation says that this hydrogen is pointing to the back of the computer, like this hydrogen here, okay? Now we can also use some other representation like a space filling model, and this is mainly used if you want to know the size of your molecule. Then you can measure the size of the molecule, or more or less approximately determine the size of the molecule. And this type here is also, this is very commonly used because it is practically like the molecular formula, but in this case, it is clear here that this hydrogen, the fourth hydrogen, is attached to the oxygen, and the other three hydrogens are attached to the carbon. So this condensed structural formula is giving me a little bit more information about the structure than my molecular formula, and it gives me less information about the structure than the structural formula, but let's say this one is in between these two, okay? Now, another way to represent my organic molecules are these. We can use the expanded formula where we represent every single bond in the molecule. So every single hydrogen, for example, is represented here, okay? Now, the condensed formula is not gonna represent the hydrogens or the bonds between carbon and hydrogens. We are just gonna summarize them like here. So instead of putting this C attached to these three hydrogens, we just write CH3, okay? This one, for example, this carbon is attached to two hydrogens, right? And to two carbons, so this is a CH2. This is one here, right? Another way we have to represent these formulas is, and actually this one is very common, is the skeletal structure. So when we use this type of formula, every single edge, like this, like this, like this, like this, represents a CH3, okay? So I know that in this edge here, there is a CH3, right? Now, each one of these points that interconnect two lines, right, are gonna represent a carbon, Now, we can easily see how many hydrogens are there because we know that, for example, in this case, this carbon is attached to three other carbons, and therefore it only has room for one hydrogen, right? Remember, carbon can only have 4 bonds, right? In this case, this carbon is attached to two other carbons, and therefore it has only room for 2 hydrogens, right? So if you want to compare this skeletal structure to the condensed, this point here is this CH3, this one here is this one here, this one here is this one here, and then, for example, let's see, this one here, that one there, and the next one to the right, which is this one here, is that one there, etc., etc. Okay? So we can represent an organic compound, an organic molecule, just using lines. All right? Okay. By the way, this one is also known as the line structure. Now, because carbon can form 4 bonds, we are going to have different combinations, or these 4 bonds can be formed in different ways. The most simple one is a single bond. So a single bond is a covalent bond in which the bond is formed by 2 electrons, and these 2 are shared. right? So for example, that one there is a single bond, and we already know that there are 2 electrons forming that bond in there, right? Now, we have also a possibility to form a double bond. So in this double bond, 2 pairs of electrons are shared to form the double bond. So we have double bond here. Each one of these contains 2 electrons. So in total, we have 4 electrons shared by these 2 carbons, right? And the last possibility is the triple bond. At this point, I guess you guys know that there are 3 pairs of electrons for a total of 6 electrons forming that triple bond. So in each one of these bonds, there are 2 electrons for a total of 6, right? Okay. Now, according to the type of bonds present in a molecule, there is a classification. The first type included in this classification is the saturated compounds. These saturated compounds are compounds formed by only single bonds, like for example methane. Okay, so methane, let me see, where is my pen? Methane is a carbon with 4 hydrogens like this, right? Only single bonds. Now, if we have, it's right there. Anyway, if we have 1 or more either double or triple bonds, then that compound is going to be part of the unsaturated compounds, right? For example, ethene. Ethene has a double bond there, and that makes it an unsaturated compound. I'm pretty sure you guys have heard this definition when talking about fats. For example, unsaturated fats are better for your digestive system. They are kind of healthier because they can be degraded easier. You don't gain a lot of weight if you eat unsaturated compounds, etc. But this is a very common word that we use to describe foods, especially fats. Okay? Now, we said that we said that organic compounds are formed by carbon, hydrogen, and some other elements. Now, we can group the different molecules according to the elements the elements contained in that molecule and the way they are arranged. So for example, if we only have carbons and hydrogens, all these molecules are going to form part of a family named alkanes, right? So if we only have carbons and hydrogens, my molecule is part of the alkane family. And all of them are going to have similar chemical and physical, well, not physical now, but similar chemical properties. Okay? Now, if we have 1 or more double bonds, we are going to name this family alkene, right? So when we have any single molecule that contains one or more double bonds, is considered an alkene. If we have triple bonds, this is an alkyne, right? Now, if we add other atoms different than carbon and hydrogen, we are going to form different families. For example, if oxygen is present in the form of a hydroxide like this, then we're going to call that compound an alcohol. All right? They belong to the family of alcohols. And once again, all of them have very similar chemical properties. If we have 1 oxygen only between two chains of hydrocarbons, then we have an ether, right? If that oxygen is in the middle of a cycle, then that's an epoxide. And if we continue like that, for example, in this case, we have a halogen. So these compounds belong to the family of the haloalkanes. And in the same way, we can define aldehydes, ketones, carboxylic acids, acid anhydrides, esters, amides, acyl halides, all right? All of these here, for example, if you see, they have a double bond between a carbon and an oxygen, all of them. However, the rest of the molecule is different. In this case, the aldehyde has a hydrogen right here at the end. The ketone has another hydrocarbon chain attached to that carbon. To be a carboxylic acid, we need a hydroxide attached to that carbon. To be the anhydride, we have another oxygen with a different ending of the molecule, if you want to say so, right? And so on and so forth, okay? Now, if instead of oxygen we have nitrogen present, which is this group here, right? We can have amines, where we only have nitrogen with hydrogens, right? Or we can have the nitrile family, where we have a carbon with a triple bond attached to a nitrogen. We can have also, amides are not here, but oh well, we can have also this type of compounds in which nitrogen is present and probably some other elements like these oxygens here, right? We can also have sulfur, right? We can also have cycles with double bonds, which are called aromatic compounds, forming what we call an array, right? So these here, or these little characteristics that define each one of the families, is what we call the functional group, right? Molecules having the same type of functional groups belong to the same family, right? Okay. So the last part, how to name my organic molecules. And at this part is very broad because, of course, each one of these functional groups have different rules to name their own compounds. As you guys have different last names, these guys have also different rules. So we're just gonna focus in this lab, we're just gonna focus to the alkanes, right? So once again, alkanes are molecules that contain only single bonds between carbon and hydrogen. That's it, okay? So how to name alkanes? First, the general formula of any alkane is this one, CnH2n plus 2. So, for example, if we have a saturated hydrocarbon or an alkane that contains 5 carbons, then the formula will be C5 to represent the 5 carbons, right? And the number of hydrogens present here would be 2 times 5, which is 10, plus 2, right? So that would be the molecular formula of a hydrocarbon that contains 5 carbons. What if my hydrocarbon contains 20 carbons? Well, this one is easy too, right? Because we have 20 carbons, right? And how many hydrogens? Well, if you thought on 42, then you're right, because 2 times 20 is 40, plus 2 is 42, and that would be the molecular formula of the hydrocarbon or the alkane containing 20 carbons. Okay? All right. Now, the first part when we talk about naming the alkanes, the first thing that we have to learn is how to name straight chain alkanes. And this is just one single chain, like this one, right? We already said this is the line, these ones here are line structures, right? And we already say that every single one of these points and every single one of these internal points contains a carbon and the respective number of hydrogens, right? So, if we have only one carbon, look at this. We are gonna use the root meth and then the ending ane, meaning this is an alkane, right? If we have two carbons, we are gonna use the root eth and the ending ane, meaning also this is an alkane. If we have three carbons, we're gonna use prop and then ane, or butane for 4 carbons, or pentane for 5 carbons, right? And the roots for 6, 7, 8, 9, 10 will be x, ept, oct, non, dep. All right? So x represents 6 carbons, hept 7, oct 8, non 9, dep 10, and all of them have the ending ane, meaning these are part of the alkane family, right? Okay. Now, the important part here is that this nomenclature, or this way to name the alkanes, is pretty easy, but it only covers the straight chain alkanes. So what happens if I have something that is not a straight chain? If it has some other little things attached to that chain. So, the way to name this type of compounds, it's as follows. We're going to follow some rules here that are going to make our job very easy, right? So, step 1. Find the longest continuous chain of carbons, and this is not always this straight chain. It's not always that, okay? We have to find the longest one. So let's say I'm gonna start here, and this is 1, 2, 3, 4, then I'll continue here, 5 and 6, okay? Now, let's say I'm gonna count 1, 2, 3, 4. In this case, I'm gonna put a 5 here and then 6. Well, these two chains are exactly the same, right? I'm gonna count now. 1, 2, 3, 4, 5, 6, and then 7. Wow, this one is longer, right? Or I have another possibility here. 1, 2, 3, 4, 5, 6, and then this one will be 7. So this chain here, the horizontal, and this chain here with this other methyl attached here, both of them are 7 carbons, okay? But I could also start from, I can start also from this carbon here, so I can say 1, 2, 3, 4, 5, 6, and that one will be shorter, so no, it's not a good example. Or I can say 1, 2, 3, 4, forget about it. 1, 2, 3, forget about it, okay? So far, this is my longest chain, all right? Or if you want that one here, I'm just gonna take this one. It's easier. Visually it's easier, right? Okay. Now let's move on. I already know the longest chain contains 7 carbons, right? Now, I have to number these carbons in the main sequence, starting with the end that will give the attached groups the smallest number. What are the attached groups? They are this one here, it's attached to that main chain, right? This one here is attached to that main chain, and we said that this one here is attached to that main chain. So if this here is my longest chain, I have 2 options. Either I consider this carbon 1 and start counting from right to left. So let's see, 1, 2, 3, 4, 5, 6, 7, okay? So my attached groups will be in position 2, 3, and 4, okay? But I can also start from this side where this carbon is 1, 2, 3, 4, 5, 6, 7. In that case, my attached groups are in position 4, 5, and 6. So if you see the way the attached groups give me the smallest numbers, if I start counting from the right to the left, okay? So I gotta keep in mind that I have a 7 carbon chain, and I'm gonna start counting from the right to the left, okay? Now, I have to add numbers to the names of the groups to identify the positions of the chain. So we said that this is 1, 2, 3, 4, 5, 6, and 7, and we said that this group here is in position 2, this one is in position 3, this one here is in position 4, right? But I also have to name all of these attached groups. How am I gonna name these groups? So let's see this table. Let's say that my attached group, and this thing here represents the main chain. In my case here is this chain here. Okay, so this chain here is represented by this here, okay? So in this case, my attached group, which by the way, I'm gonna call it from now on the alkyl substituent, right? So this one here contains 1 carbon, right? So if you remember, for 1 carbon, I use the root meth, right? Methane, if that was an alkane. But in this case, this is an alkyl substituent. So instead of adding the ending ane, I'm gonna add the suffix YL. And this one becomes methyl, right? Now, for a substituent with 2 carbons, 1 and 2, remember, I have to use the root F, but instead of ane, I'm gonna add YL, ethyl. If I have 3, 1, 2, 3, this is gonna be prop, and then the ending YL, propyl. And then in this case, for example, I have 1, 2, 3, 4 carbons, a substituent with 4 carbons attached to my main chain. So remember, the root for 4 carbons is but, and then YL, butyl. In this case, I have 1, 2, 3, 4, 5. The root is pent, and my substituent becomes pentyl. This one has 1, 2, 3, 4, 5, 6. So this is an hexyl, etc., etc., etc. If it has 7, then it's heptyl, octyl, nonyl, decyl, etc. Okay? So we said that, no, let me go back here. So this one contains 2 carbons, therefore this is an ethyl. This one is a methyl. This one is also a methyl. Okay? Now, it says there, these numbers become prefixes to the parent chain. So that means that I have to write the numbers and the names before the name of the main chain. So I have a 2-methyl, right? This is one here. I have a 3-methyl. That's one there. And I have a 4-ethyl, right? Is that one there? Okay? And my main chain is 1, 2, 3, 4, 5, 6, 7 carbons long, so that is a hept, 7 carbons, and then the ending 8, right? So far, this is what I have. Okay? Now, in this case, if you see, I have 1 methyl here and another methyl here for a total of 2. I am not gonna say 2-methyl, 3-methyl. I have to use another prefix. So, if I have 2 of the same substituents, I'm gonna add the prefix di, meaning 2, right? If I have 3, I'm gonna add the prefix, tri, right? For 4, I'm gonna add tetra. For 5, let me put it here, I'm gonna add penta. If I have 6 of the same, it's gonna be hexa. 7 of the same, hepta, octa, nona, deca. Okay? So in my example, I have 2 methyls, right? So instead of writing 2-methyl, 3-methyl, I'm gonna say 2,3-dimethyl. Okay? So let's see. I have in position 2 and position 3 dimethyl, meaning 2 methyls, one in position 2 and the other one in position 3, right? And I also have a 4-ethyl, and my main chain is an heptane. Okay? Now it says there, once I have everything, I have to list the alkyl groups, this one and this one, in alphabetical order. Now for the alphabetical order, I will not take into account that prefix. And if you see, E comes first or before M, right? So this is a 4-ethyl, and then this is a 2,3-dimethyl, right, in a heptane chain, all right? We're almost there. The only thing that we have to make sure we're using is punctuation. So it says, use commas to separate numbers and hyphens to separate numbers and words. Okay? And then I'm gonna see the last, no, I thought there was another one, but no. So, between numbers, I have to use commas, and that was the reason I separated 2 and 3 with a comma. Then, Again, for ethyl, and because this is a number and a word, I use a hyphen. Then the next is my two numbers representing the two methyls, right? So a hyphen here because this is a word and this is a number. A hyphen here because this is a number and this is a word. But between my numbers, I have a comma, all right? Now, at the end, I have to add the name of the name chain. And for that, I'm not gonna use commas or hyphens. So I'm just gonna write here my main chain, okay? So the name of this compound is again for ethyl 2,3-dimethylheptane, okay? Let's do these exercises here. So remember, the first step is to find the longest chain. So let's see. 1, 2, 3, 4, 5. That's a possibility. Let's see. 1, 2, 3, 4, 5. That one is exactly the same. Let's count starting from here. 1, 2, 3, 4, 5. What's the same? So really the longest chain has 5 carbons, right? Look at this. 1, 2, 3, 4, 5. Again. 1, 2, 3, 4. Now. 1, 2, 3. Now. 1, 2, 3, 4. Now. So really the longest chain contains 5 carbons, right? So I'm gonna say that this is my longest chain. 1, 2, 3, 4, 5. Then step 2, I have to start counting the carbons in my chain, starting with or assigning number 1 to the carbon that produces the smallest numbers for the attached groups. So this is an attached group, this is an attached group, this is an attached group. If I start from this carbon, the first attached group is in carbon number 1, 2, 3, 4. So I have in carbon 3 and in carbon 4, I have attached groups, right? But if I start counting from this carbon here, then it's 1, 2. That's better, no? 1, 2, 3. So 2, 3 is better than 3, 4, no? So this is gonna be my carbon 1, 2, 3, 4, and 5. Okay? Now, I have to assign numbers and names to my substituents. So for example, this one here is a methyl, right? Because it has only one carbon and is in position 1, 2, 3. So over here I have a 3 methyl. Over here, this is a methyl 2, right? In position 2. And over here, I have a substituent with 2 carbons. So this is an ethyl, right? And it is in position 3. Okay? Now remember, these two are the same methyl. So I can say this is a dimethyl. Okay? And they are in position 2 and 3. Now, I have to organize these or order these in alphabetic order. And we already said that E comes before M. So the name of my compound would be 3-ethyl, and hyphens between numbers and letters or words, right? And then 2,3-dimethyl with comma between numbers and hyphen between numbers and words. And then I have to name the longest chain, which contains five carbons. So this is append A. And remember, between the last substituent and the main chain, we do not add any hyphen, comma, or any, right? So this one here is a 3-ethyl 2,3-dimethyl pentane. Okay? Let's see this one here, right? Once again, we know that in every single one of these points, we have a carbon and the respective amount of hydrogens, right? So, which one do you think is the longest chain? All right, I hope you said this one here, right? It's kind of visually easy to see because, let's see, this one has 1, 2, 3, 4, 5, 6, 7, 8 carbons, right? 1, 2, 3, 4, 5, 6, 7, what? 1, 2, 3, 4, 5, 6, 7, 8, right? We can have also 1, 2, 3, 4, 5, 6, 7. That one is shorter. Or 1, 2, 3, 4, 5, 6. That one is shorter, right? So we all agree that this one here is my main chain. Okay? Once again, we have to add numbers to my carbons, starting by the carbon that produces the smallest number for the substituent. So if I start from here, it is 1, 2, 3, 4. The first substituent is in carbon 4. If I start from here, is 1, 2, 3, 4. Same thing, right? So it doesn't really matter. Plus, I have here an ethyl, right, with 2 carbons. This substituent is an ethyl, and I have here an ethyl, right? So it doesn't really matter which carbon I use as carbon 1, right? Because both of them are in position 4. I mean, the main one is in position 4. So this is, let's say this is 1, 2, 3, 4, 5, 6, 7, 8. Okay? So because I have 2 ethyls, the name is going to contain diethyl, right? And these are the only substituents, so that's the only ones that I'm going to add there. But I have to add the position. One is in carbon 4, the other one is in carbon 5. So this is 4, 5. And my main chain has 8 carbons. So this is an octane, right? Once again, commas between 2 numbers, hyphens between numbers and words, and at the very end, nothing. Okay? Last one. Let's see this. So I think visually looks like the chain would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Kind of looks right now because let's see, 1, 2, 3, 4, 5, 6, 7, 8. So this one here now is shorter. What would be another possibility? 1, 2, 3, 4, 5, 6, 7, 8. No. So I guess, guys, you agree with me that the longest chain is this one here. And notice that the longest chain doesn't have to be horizontal all the time, right? Over here we have like a vertical part, a horizontal part, a vertical part, right? But the main chain has to contain the most, or has to be the longest possible chain in that molecule, okay? Step number 2, we have to start giving numbers to these carbons, starting by the carbon that produces the smallest number of the attached groups. So I have a methyl here, I have an ethyl here, I have a methyl there, and I have a methyl right there, okay? So let's see. If I start from this carbon, it's carbon 1, 2, 3, 4. My first methyl would be in position 4. Let me put it here. And then I will have substituents in 5 and 6, right? So if I start from this carbon at the bottom, the substituents will be in position 4, 5, and 6, right? Now let's say I'm going to start from this one. So this is 1, 2, 3, 4, 5. So the first substituent is in position 5. These are in position 6. This one here is in position 7, right? So if you see, guys, if I start from this carbon, my substituents are going to produce smallest numbers, right? So this is carbon 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, okay? Now, let's see the substituents. This one here, and this one here, those three are methyls, right? I'm gonna, let me see, where should I write it? I'm gonna write it here. So these three are methyls, and I have 3 of them. So I'm gonna add tri, right? Now, these ones are in position 4, 5, and 6. 4, 5, and 6, right? Now, I only have to name this ethyl here, right? And we say that ethyl comes before methyl, right? So this ethyl is in position 5. So this is 5 ethyl, right? So it's 5 ethyl, 4, 5, 6 trimethyl, and then the name of the long chain, which is decane, because it has 10 carbons. All right? Once again, hyphens between number and words, comma between numbers, and at the end, nothing. Okay? All right, guys. So this is all for today's video. You can find more exercises about nomenclature in your book. At the end of chapter 21, you find some of them. You have the answers to some of those, the odd or the even, I can remember. Also, if you look online, there are plenty of exercises there about nomenclature with an answer key. You have to practice this because, as I said at the beginning, this is included in your final exam, right? Okay, guys, so I'll see you later in some other lecture. Well, I don't know. At some point, I will see you. Okay? Bye-bye.